Topic 15, Energetics, Thermochemistry. 15.2, Entropy and Spontaneity, higher level. Here are the objectives for this topic. So does this look familiar to you? Is this your room? If so, then you've already got a pretty good idea about what entropy is. Entropy is disorder, it's a mess. Now in chemistry, entropy is given the symbol S, and it must be a capital S. It is the measure of the distribution of total available energy between particles. Now the greater the disorder of the particles, the greater the entropy, the bigger the number. Now disorder is more likely than order. It's more easy for things to be in a mess, all over the place, than it is for them to be nice and ordered and structured. Now a system, such as a room, or it could be a chemical reaction, is in a high state of entropy when its degree of disorder is high. What that means is, entropy is a number. If it's got a big number, there's a lot of disorder. So high entropy is going to have a big number. So for better or worse, nature likes disorder. It likes to have a high entropy. So it likes chaos and it likes disorder. So in fact, much of our lives consist of fighting this disorder. So whilst nature is trying to move towards the chaos, we're trying to sort everything out again, and that requires energy and effort. So if we look at these two diagrams now, the one on the left is with two gases, and we can see the particles nicely separated between the red and the green. And then the one on the right, we can see the particles are now all mixed up. Now we can explain entropy using probabilities. The one on the left, they can only exist in that form. They can only exist separated. Now, whilst the individual particles in the red and the green can move around, they'll never be mixed. So there's one arrangement, and that's separated. But when they're allowed to mix with one another, the possibility for different arrangements becomes 2 to the power of 20. Now, if we think about it in terms of which one's more likely, we've got one potential arrangement versus 2 to the 20. The spontaneous direction of change is from a less probable to a more probable state, and that's demonstrated in that diagram. Now, states of matter is a good way of looking at entropy. So the diagram on the left, this is looking at liquid bromine to gaseous bromine. Now in a liquid, the particles are close together, but they can move over each other, whereas in a gas, they're nice and spread out and separated. Now, when they're separated, they're considered to be more disordered. They're much more random in terms of their motion. The same is true with water going from a solid to a liquid. Now, a solid, nice and structured, nice and rigid, particularly due to the hydrogen bonds. Then as soon as it goes to a liquid, the entropy increases because they can now move over each other. This can be shown nicely from a phase change diagram. So on the x-axis we've got temperature increasing, and entropy on the y-axis goes up as we go from liquid to a gas. And we can see the same, but not quite as pronounced, going from a solid to a liquid. Now you'll notice there's a very, very sharp jump in entropy during the phase change. Okay, so there's a steady increase as temperature goes up, and that's just because the particles are moving around more, they're more excited, more energy, so moving around and hitting each other a bit more. But then there's a very big jump as soon as we get the phase change. So immediately when we go from a liquid to a gas, there's a big jump. So entropy and temperature. So the entropy of a substance increases with temperature. So as we just seen on the previous graph, there's a very steady increase in entropy as temperature increases. And that's because the particles are moving around more. If we look at this heptane molecule, which is a carbon of length 7, it's a carbon chain with a length of 7 carbons, it can move around more, it can rotate itself more. Okay, so there's all the different motions it can have. And that's easier at higher temperatures, so it's more disordered. Now we can predict entropy changes, so the change in the number of gaseous particles is usually the largest factor to be considered. So even if a comparable reaction has a greater increase in total particles, but these particles are still in the liquid or solid state, that won't have the same effect on entropy as if we were going from, say, a solid to a liquid, or a liquid to a gas in particular. We can calculate entropy using this equation. So we've seen products minus reactants before when we've looked at enthalpy. And it's the same for entropy. So the entropy change is the sum of the products and their entropy minus the sum of the reactants at their entropy. But the units are different to enthalpy. The units of entropy are joules per Kelvin per mole. Okay, joules per Kelvin per mole. Now, if you ever struggle with the units, you'll be able to find the values and indeed the units in the data booklet for the IB. Now, an increase in disorder produces a positive delta S. So a nice big positive value means that there's an increase in disorder. So examples of reactions where we see this are decomposition, so a substance decomposing, changes in states, as we've already discussed, dissolution, so a substance dissolving and then giving out heat, and just general increases in temperature, so exothermic reactions. Standard entropy calculations. So at the top we can see A plus B goes to C plus D. They're the capital letters. The lowercase letters represent the stoichiometry, or the moles of the reaction. Now, entropy change calculations can be calculated, as we know, products minus reactants, and we can see this applied for the particular equation on the top. Let's look at a problem. Calculate the standard entropy change for the following reaction. So this is a formation. So formation is formation of 1 mole of a substance from its constituent elements in their standard state, standard conditions, and here we've got hydrogen gas plus half of an oxygen gas becoming water as a liquid. So that's a formation. These entropy values, they can be read from the data booklet table, and you'll notice the units are joules per Kelvin per mole. As we know, it's products minus reactants, the sum of. So we add up the sum of the products, which is just water in this case. But then we'd subtract the reactants and the sum of the reactants. But as you can see from the equation, we only have half of an O2. Therefore, we must multiply the entropy, in this case 205.1, by a half. That reflects the stoichiometry of our equation. And you can see here we've only got 1 mole of the H2, so we don't need to do anything to that value. This can then be worked out to give us our entropy value. Now in this answer you can see we have a negative value. So that tells us the system is becoming more ordered. That makes sense because if we look, our reactants are 2 gases and they're forming 1 liquid. So it would make sense that 2 gases would form 1 nice ordered liquid. So the gas particles floating around, very disordered, very chaotic, forming a nice liquid. Gibbs free energy. So this is given a nice capital G. And this is the energy available to do work. Now we've got a new equation here. Delta G equals delta H minus T delta S. And the T delta S, that is a multiplication there. So it's temperature multiplied by entropy change. Now temperature is in Kelvin, and that's very important for this. It has to be in Kelvin. Now the value of Gibbs free energy tells us something very interesting. It tells us if a reaction is spontaneous or not. Now if delta G is negative, the reaction will be spontaneous. That means it will occur naturally, quite easily. Now it might require a spark, it might require an initial bit of energy to get going, but it will spontaneously occur. Whereas if delta G is positive, the reaction will not be spontaneous. For any individual element which is in its standard state, we consider delta G to be 0. Now the reason that's important is because you will see in the table in the data booklet for delta G, no standard element is mentioned, and that's because the values are 0. Now here are the equations that you will need to calculate Gibbs free energy. We have delta G equals delta H minus T delta S, but we also have our enthalpy, entropy, and Gibbs, products minus reactants. Now spontaneity. So depending on the sign of delta H, delta S, and delta G, that will tell us whether it's ever possible for a reaction to be spontaneous. Let's look, for example, at the second one down. If delta H is positive, so it's an endothermic reaction, and delta S is negative, so the products are more ordered than the products. The fact that delta H minus T delta S, that will always give us a positive value, because the minus T delta S, that's two negatives there, a negative delta S, a negative in the equation. And then the delta H is positive, so we're adding two positives together now. So delta G will always be positive. The reaction will never be spontaneous. The opposite is true in an exothermic reaction, and where delta H is positive, so the products become more random. This type of reaction will always be spontaneous. Delta H is going to be negative. We're then subtracting a positive value, so again we're going to retain that negative. Now it might be large, it might be small, the magnitude, but it will always have that negative sign. Again, this is just going to help you summarize that information a little bit more clearly. So please do have a look at this table. Let's look at a problem. So calculate Gibbs free energy change of reaction for the combustion of ethanol. So combustion. So we want to start with the equation. We want to start with our equation. So the combustion of ethanol. It burns completely in oxygen to produce carbon dioxide and water, and we must balance the equation. So the stoichiometry here is 1, 3, 2, 3. Now, you will see from the data given in the question, we have the Gibbs of ethanol, carbon dioxide and water, but not O2. And that's because, as we know, for a standard element in its standard state, Gibbs is 0. We're then looking at products minus reactants. So it's a simple substitution, but we must take into account the stoichiometry. This will then give us our final value. So as we know, a negative value tells us that the reaction will be spontaneous. And that makes sense for a combustion. We know that a combustion will naturally occur. That is the whole point of ethanol as a fuel, for it to burn. Next up, determine if the following reaction will be spontaneous at 298 Kelvin. We're also given enthalpy values and entropy values. So we're looking here at ethane, and this is becoming ethene and hydrogen gas. We're going to need delta G equals delta H minus T delta S, and we can substitute in our values. But please note that delta S has been divided by 1000. This is so that we can turn joules into kilojoules, and this is essential. In doing so, we will end up with Gibbs free energy as a positive 101 kilojoules. And as this value is positive, the reaction will therefore not be spontaneous at 298 Kelvin. What we could do is change the temperature, and changing the temperature would influence the spontaneity of this particular reaction. Now this final slide here, what this does is it shows the point at which Gibbs free energy is at a minimum, determines if a reaction goes to completion or reaches a balance of reactants and products, and we term this equilibrium. Now we will be looking at equilibrium in a lot more detail in topic 6. But if Gibbs is at 0, we don't know which side it's going to fall on. Is it going to fall on the side of the products or the side of reactants? And that's why we need to consider equilibrium, and we'll be moving on to that. Here are the objectives, just to summarize what we've covered in this particular screencast.